Hey Algebra 2, here's the lesson notes for 5.4 regarding imaginary and complex numbers. So the first thing we're going to do is just remember how to simplify those square roots. So if I have something like the square root of 50, the first thing I'm going to do is break it down into its factors. And the smallest factors of 50 are 2 and 5 and 5. Well, when I have something like 5 squared, and it's in a square root, the square root basically undoes it, and I can pull that pair out and leave whatever is left over on the inside. I do the same thing for 450. This one takes a little bit more. This breaks it down to 225. I believe it's 2 and 5 and 5 and 3 and 3. Let me just double check that real quick here. 2 times 3 times 3 times 5 times 5. Yeah, there we go. So we are right there. So when I look for my pairs that I'm going to pull out here, I get to pull out a 5 and I get to pull out that 3. And once they're out there, since I know they're multiplied, I'm just going to multiply them and simplify it like that. When we have something in a fraction like this, we can actually split the square root up over the top and the bottom and simplify it like that. Now, square root of 11 can't be simplified, but square root of 49 can be to a 7. Technically a plus or minus 7, but I'm just going to give you that final answer there. You could put a plus or minus out in front. Alright, on this top piece, we can do the same thing, say square root of 32 over square root of 81. Well, the square root of 32 can actually be factored into to 5 sets of 2, actually, I think. So our final answer on top is going to be 4 square root 2, and our answer on bottom is going to be 9. Of course, plus or minus, if we're going to be precise, we should be putting that out front. Notice I can't simplify this at all, but if these were, if they had something in common, I would try to factor that out and make it more simple. What happens, however, when I get something with a negative square root? Well, we don't really have any any one number that multiply together to equal negative 1. And I'll show you what I mean by that. 1 times 1 is positive 1, right? Negative 1 times negative 1 is positive 1. So what numbers exist that could get me to negative 1? Well, there are no such real numbers. So what we went ahead and did as mathematicians is we created this imaginary number, this I, that in reality basically says I times I is negative 1. And it's imaginary because these numbers don't actually exist, but we need them to for math problems like this one that I gave you here. So if you're writing this piece down, I itself is the same thing as the square root of negative 1. And it might help if we start by making a chart. So what is I to the 0? Well, any number to the 0 is just going to be 1. What is I to the 1? Well, any number to the first is just that number. What is I squared? Well, remember how we said I is just the square root of negative 1? Well, if we take I squared, that's I times I, our final form is 1. Well, what is I cubed? It's the same thing as I squared times I to the first, or negative I. And what I've done each time here is I've multiplied I. So I'm going to go over in my little roundhouse wheel over here, and I'm going to say each time I move on my wheel, all I've done is multiply by I. And you'll notice that this is a continuing cycle. So if I multiply this by I to the 4th is the same thing as 1. It's also the same thing as I squared times I squared, or negative 1 times negative 1. I to the 5th then can be I to the 3rd times I to the 2nd, which is going to be, just in case we weren't paying attention, I, yes. And then if we keep going, we get negative 1 and negative I. And notice, no matter how many times we do this, this cycle is going to continue repeating. So if I ask you specifically about an imaginary number to an exponent, we can figure it out without sitting here and creating a table that goes all the way up to I to the 26th, or later, I to the 425th. And the way that I like to solve these is trying to figure out how I can get to this exponent as easily as possible using this table, this simple set of values that I have. Which is the nicest one of these to use? Well, I to the 4th equals 1. If I can calculate things with 1, I want to. But how do I go from I to the 4th to the 26th? Well, if I take I to the 4th and I raise it to the 6th exponent, I get I to the 24th. That's pretty close, and then all I'd have to do is multiply by another 2 i's, right? And the reason that I did this was that so when I simplified, I used I to the 4th because I knew it was the same thing as 1. And 1 to the 6th is just 1. And I squared, I already know that one is a nice one as well, so why not use that? When I simplify this out fully, I get -1. I strategically used I to the 4th in order to get to the exponent I care about. Now, there's a lot of different ways to do this, but if I can use I to the 4th, I'm going to. So when I have I to the 425th, I want to do the same thing. I want to say, how close can I get to 425 using the number 4? Well, if I take 425 divided by 4, it goes in 106 times. And 4 times 106 gets me to 424. I'm now only 1 I away, so all I have to say is multiply by a single I. Again, I strategically chose that so that when I multiplied, 1 to whatever exponent in the world is still just going to be 1. So I've strategically chosen the easiest value to simplify. When I get all the way said and done, because I can't simplify I any further, my final answer for I to the 425th is just I. And there aren't going to be a lot of these, but again, this process of trying to figure out what exponent raised is a lot faster than sitting here and going around your circle or making this table. Alright, let's keep going. The problems here are going to be a little bit more commonly. So if I give you the square root of -98, I'm going to break it down into its factors just like I normally would. I'm going to break it down into -1 and then into 2. That gets me, I believe, to 46. Yeah, if I'm not mistaken. 46 divided by 2 is then getting me to 23. I feel like there's a nicer way of doing that, though. Let me double check here. Yeah, it was 49, my bad. So this is actually times 7 times 7. 49, not 46. Alright, when I take numbers out, well, I know that the square root of -1 is I, and I can take this pair of 7s out, and then I just leave what's left over. And that is my final answer. I can't simplify it any further, so that's what I leave. Over here, I do something very similar. The first thing I see here, though, is if I see a negative in here, I automatically know that I'm going to be able to take an I out. I could have said that same thing over here and just said, oh, it's I times the square root of 98, and then factored 98 out. Either way works. For this one, I'm going to do it where I take it out first, because then when I square it, we're going to get 3i times 3i, or 9i squared, and then square root of 5 times square root of 5 is 5. Now I know what each of these are because I know that I squared is the same thing as -1. Well, what is 9 times -1 times 5? It's -45, and so that is my final answer. This one over here, again, I can take my I out, take it out in the second term as well. This becomes 2i, this becomes 3i, I get 6i squared. Not my most simplified version, so I have to keep going, and I have to say this is -6. You always want to try to get it down as far as you can. You don't want i's if you don't have to have them. Sometimes they will be necessary, but if we can get them without i's, that's what we want. Excuse me, forgive my coughing today. Alright, so if we're going to simplify these expressions, same thing. We're going to have 8i squared, which is the same thing as -8. Here, something really cool happens, because what we're multiplying by, in this case, is the conjugate. That vocab will come up a little bit later, but for right now, just something good to know. The conjugate essentially says when we multiply, we're going to get 9 -15i plus 15i minus 25i squared. And the conjugate just means that these middle two terms are canceling out. That's really nice because they have canceled the only two terms with singular i's. This means when we simplify, I squared becomes positive 25. I'm left with no i's whatsoever, which is what I want to be left with. Alright, next one. I see a negative. My favorite way is to just pull the I out and then deal with the rest of what's in the square root. In this case, this is going to be 2 times 3 times 3, or 3i square root 2. This one is as simple as it can go because it only has one I left. Alright, last one, pull the I out. When you have two square roots multiplied by each other, you can multiply their pieces inside. So this is going to be 2 times 2 times 5 times 3. The 2's come out. We multiply everything left over, and our final answer is 2i square root 15. Alright, next up, we have something like this. Well, how are we going to solve something like this? It's not in a difference of squares, it's not in a difference of cubes, it's not in a sum of cubes, it's none of the forms that we're used to. So what we're going to do here is solve for x squared in our, I guess I would call it the common sense way. Just try to get x by itself. We do that by moving the 48 over, by dividing both sides by 3, and then by taking the square root of whatever is there. In this case, when I do that, I pull an I out and I take the square root of 16. And because I've taken the square root of something, it's going to have to be a plus or minus of whatever it is. So in this case, it is x equals plus or minus 4i. Now something very similar happens in the second one. I get x squared equals negative 25. I get x equals plus or minus the square root of negative 25. And when I finally take this, I get plus or minus 5i. And the reason that I know I couldn't do a difference or difference of squares, or over here sum of squares, one, because sum of squares doesn't exist, but also because if I can simplify it by just moving things to one side, because there's no pesky x term in the middle, I do want to do this the easiest way possible. I don't want to have to go through using those formulas if I don't have to. Alright, every number containing only I is called purely imaginary. What happens when we combine imaginary numbers? We get something that looks like this. We have a plus bi, where a is the real part, and bi is the imaginary part. And this together is called a complex number. Which you can see a little bit more about over here. So the big idea for this is let's immediately do an example here. Find the examples for m and n that make the equation true. Well, this piece here is the real part of the left side, and this is the real part of the right side. This piece, because it's attached to I, is going to be the imaginary part of the left side, and this 5 attached to I is going to be the imaginary part. So what I can do here is I can set my real part equal to my real, my imaginary equal to my imaginary, and now essentially what I have is a system of equations which I know how to solve. I'm going to solve this by leaving the first one and multiplying the second one by 2, because when I do that, I get negative 2m, which is going to cancel that out. So my middle terms cancel, and I get 5 equals 15, m equals 3. I'm going to use that and plug it back into my first equation and solve to get n equals 1. Once I have this information, I'm going to put it in that coordinate point and call it a day. And this problem is as simple as just saying real equals real, imaginary equals imaginary. Alright, almost done. So, subtracting and subtracting complex numbers seems really convoluted, but it's not. These parentheses don't actually do anything for us. They don't change the equation if I take them out, because there's nothing in front of this one that would change it. So when I have this, the same way that I set my reals on the other page equal and my imaginaries equal, I'm just going to add my reals and my imaginaries here. 6 plus 1 is 7, negative 4 plus 3i is negative I, and that's my final answer. That is as simple as it gets right there. This next one is very similar, except the parentheses do something for us here. We actually have to make sure that we distribute this negative before we go any further. So it's going to be negative 5 plus 4i. But once we get here, it's the exact same idea. 3 minus 5 is negative 2. Negative 2i plus 4i is plus 2i. And that's as simple as it gets. I mean, it really doesn't get any easier when it comes to imaginaries. Final concept. Whew. I know this has been a long video too, so I'm just as eager to get done with it as you are. So first, a little terminology. What is the conjugate of 8 minus 2i? Well, the conjugate here is 8 plus 2i, and I talked about this a little earlier in the video. Why is it special? It allows our middle terms to cancel out. So it allows middle terms to cancel. And we really like this in each of our problems. So what does this look like in an actual problem? Well, it gets a little more obvious down here, but if we start out, we don't just want to have these floating singular i's around if we can help it. Let's scroll into this just a little bit. And the way that we get rid of them is by multiplying by a big fancy 1. Now, I've done this before, but if it's been a while, the easiest way here is if I multiply by I over I. That's just a big fancy 1, so it doesn't actually change our equation other than the way it looks. When I multiply in here, though, what I get is 3i plus 2i squared over 4i squared. And you might be thinking, Miss Burry, why did you do that? It just made it look more complicated. Well, hold on, though. When I do this and when I simplify it, the 3i doesn't simplify at all, so I have to keep that. But I know I squared is the same thing as negative 1. So my positive 2 becomes a negative 2, and on the bottom, I get a negative 4. What this has allowed me to do is get the I out of the denominator. The same way that we don't like radicals or square roots in the denominator, we don't like i's if we can help it. So the same thing on this next one, 5 minus I over I. I don't like this I in the denominator, so I multiply everything, and I get 5i minus I squared over I squared. This one in particular becomes 5i plus 1 over negative 1. And if I want to simplify that even further, I can just divide the two tops too. Not going to tell you how I'm doing these, just going to Notice here, instead of leaving it as I squared, I automatically put it as a -1, just to save myself some time. I can't really simplify this other than the top piece, so I'm going to say 1 plus 3i over 2. That's about as simple as I can make it. Alright, last one. Excuse me. All I did here was I foiled this out. It looks really awful, but it's because there's so many square roots in the top there. And then on the bottom, we just have 2 minus I squared. Alright, let's simplify this. Alright, so I know that my square root of 12 becomes 2 square roots of 3. Thanks for bearing with me while I have my coughing attack here. -3. I know I can combine those. I'm going to bring the denominator back here in a minute, but for right now I'm just going to leave it alone. 2 minus 1 square roots of 3. So I have square root of 3 plus 2i square root 6 all over 3. That is my final answer. Alright, I know this was a long video. If you have any questions, please let me know.